So you're using a new, something new, a new quantum effect, or using quantum effects to try to do something. Instead of just on, actually you can use quantum effects to do something, to perform a classical standard functions. That's like, say, what a transistor does. It's based on quantum effects in a sense because it's microscopic, but actually the actual operation is classical. The device is classical. So quantum information is supposedly doing something not just based on quantum physics, but also the actual operation depends on something quantum mechanical. So something more exotic, perhaps something more, something different and more powerful you can do. Quantum information. Because the old one, I think, is useless in practice. The new quantum cryptography is just to try to do cryptography efficiently and securely, which, at least efficiency-wise, that was the original reason why I started working on quantum cryptography, is cannot be done efficiently before. And now we came to realize that the old quantum cryptography is not even secure in many sense. Well, BB84, the basic principle is this disturbance information trade-off. That is that you need to make intrusion level estimation, not just detect somebody is disturbing the system, but actually estimate that somebody at the level of the disturbance, so that you make sure you have a better channel than the other person. Because of it has to operate on a microscopic level, so it makes it inefficient. And it is actually not secure because of the many side information available to the attacker. What I call the KCQ principle, the key to communication in quantum noise, which includes Y00 as a special case, is that a new principle is being used for key generation that is based on something you know very well, the optimum quantum receiver principles. That is, there is not the best quantum measurement for detecting signals depends on the actual signal set being used. There is no overall measurement, which is good for different signal sets. So with this principle, we don't need to do intrusion level estimation and avoid a lot of the pitfalls of BB84, and we can also use large signals in some cases, and so avoid an inefficiency problem. For direct encryption, however, so far we only are using the quantum noise as a fundamental randomization of the system. Whether exactly how good it is with the Y00, which what you are thinking about most of the time, it still needs to be further developed and further quantified for direct encryption, which is different from key generation. Anyway, this whole issue is very muddled. There are many factors involved and lots of misunderstandings in the community. It's between whether one's talking about direct encryption or key generation, whether one is talking about what kind of information theoretic security or what kind of security it is, what kind of complexity-based security, and what is classical, what is in principle quantum, what is in principle classical. There are many factors intertwined and huge confusions in the field. And part of the problem is because in standard cryptography, actually there is no real foundation. People usually, in practice, just base everything on complexity. There is no quantitative, quantifiable performance security level. And the Shannon theory is very limited. It doesn't elaborate on the appropriateness of the entropy criteria in general, and it doesn't deal with long plain text attack even for just direct encryption. So that's part of the reason why quantum cryptography with quantum effects on top of it is quite a big mess. I think it is practically quite secure because it gives the physical layer encryption, which is hard to attack. It gives at least a random cipher, even if you get a perfect ciphertext, and which is not possible with, or not practical if you use standard encryption, because that would take up too much data rate or bandwidth. So I think it has great potential for commercial applications. And with further analysis like for example, my student Ransif and I are working on some military applications or some other special applications we may want to have high security. So that still needs to be further developed. But there is also the problem of key generation, as I said, that for key generation, it can also do key generation and so do both encryption and key generation in one system. You mean this quantum cryptography? Just something that is going to be used in widespread use, physical layer encryption from quantum. Not only quantum, because that will require optical systems. My dream is that it will be useful. It will be used, actually developed and used at radio frequency, and provide physical layer encryption in everything, involving, including the internet, the Ethernet, the cell phones, and everything, both the computer connections and computer systems.